Hello, I hope you guys can hear me. Let me just set up my chart. I'm going to be learning calculus again. My last two streams were very glitchy. I hope this stream doesn't have the same problem. So I'm going to be relearning some of the things, especially the fundamental theorem of calculus. Maybe do some exercises as well. Also, I deleted my last two calculus streams. Wasn't really satisfied with them. Okay, let me just change to full screen. Okay, fundamental theorem of calculus. The answer key. Okay, so this is what I remember. Let's say there's a graph like that, and then we have this a x is a variable, t y, this is f of t, right? Okay, so this area over here is capital F of x, and then x is a variable. So the first fundamental theorem of calculus states that the derivative of the area is equal to f of x. So this is the area. So the derivative of the area, so how much the area is changing at this point, that is equal to f of x. So let's say here this is dx, but dx is like infinitely small. I don't know if that's how you say it. So like it is smaller, 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 infinitesimally small, I think. So how much the area changes for a very tiny increase in x, that is approximately equal to f of x. So first of all, the definition of this is that f of t dt. No, why is this not loading? Right. Um, and then so yeah, so the derivative of this is equal to limit, by the definition of the derivative, the area plus h minus f of x over h. Let's call this h, and then h is going to 0, closer and closer to 0. and this is equal to uh, x plus h 0. So okay, my OBS disconnected. Wait, let me go to YouTube and actually see if my stream is working. This happens very commonly, like it happens a lot. I'm using one very old laptop to stream. I don't have a powerful computer. To stream. I don't have a powerful computer. Okay, let me go back. Right. So I was here. So this we can expand. F of t dt plus x plus h, and then subtract it, basically this part. So basically what I'm doing, the area from a to x plus h is the area from a to x, and the area from x to h, x plus h, and then this and this cancel out. So we are left with or we can write this as, can write it like this. Now, before I go any further, I just want to explain one thing. If I have a graph, areas A and B, let's draw, whoops, something like this. A, B. So the area over here, the area over here would be, let's call this G of T. The area over here would be A to B G of T dt. But no, not this. Suppose I have an average G of T, which is like over here. Yeah, I should draw a line. This is like G of C. So G of C is the average between g of a and g of b. So let me is average g of t on a to b. So this is the average. So the area of this the area of hold on, is this is g of c b minus a, and the a basically the average area over here is equal to the area under the curve. Basically what I mean is this is equal to g of c b minus a, where g of c is like the average. So if I make g of c the subject, I can write it like this. This basically means g of c is equal to the area under the curve divided by the interval, which is b minus a. So now going back to our limit over here, notice from x to x plus h, and we are dividing it by h. So x to x plus h. So the area over here divided by h. And this will give the average f of t between x and x plus h. So this over here is equal to limit the average times it by h, which is the interval. Like, I hope you guys understand what I mean. Not times h, sorry. So the average value is the area divided by the interval. Same thing for f. The average value between these two is the area divided by the interval. And if h is going to 0, so if the area is smaller, so h is, hold on. So if the area is going closer and closer to 0, the average value of f would be equal to f of x. And that completes the proof, this proof. Now the second fundamental theorem of calculus is that a graph here, I have a constant c, I have three constants c, and then the area under the graph is g of x. X is between, I think I should do it like this, between a and b. So g of x is the area g of x is basically the area over here. area from C to wherever x is, and then x is the variable. So the second fundamental also wait I should also add that f of t, this over here is t. I should actually call it a of t is equal to this is the antiderivative of hold on, I made a mistake here. Anti I should write the text. Antiderivative a of t is the antiderivative. If you take the antiderivative of a of t, you get f of t. So basically, a of t if you derivate this, you get a of t. So the second fundamental theorem of calculus is that this area a b f of t dt is equal to the antiderivative at b minus the antiderivative at a. The antiderivative with the value of b and the antiderivative with the value of a. So like the derivative of x squared is 2x. The derivative of x squared plus 6 is also 2x. Derivative of x squared plus 7 is also 2x. Basically, derivative of x squared plus any constant c will always be 2x. So if you're taking the antiderivative, if you have 2x and you're taking the antiderivative, it's going to be x squared plus c, because we do not know this. Basically, another way of seeing this is if you have a graph, derivative tells you the tangent line. I don't know if this looks good. It's almost straight. I should do this again. Let's call it v. This is f v. So this derivative so the derivative gives you the gradient. But if you knew the gradient, the formula for the gradient, you can get the shape of the original function back, but you cannot get the y-intercept. So the function could be this or this or this. So the constant, the y-intercept is unknown. So what I was saying is, yeah, going back to this, we know that this area in between is basically g of b minus g of a. And the antiderivative, like in terms of integral, the antiderivative basically means we know that the endpoint of the area is b, but we don't know the starting point. So the starting point could be anywhere. The endpoint is over here. So a of b gives the area from an unknown starting point to b. Area antiderivative, this antiderivative at a gives the area to a, but the from is unknown. But uh, if we are finding the area from a to b, we don't need the from part. So basically, even if let's say g of x was the area from here to x, g of b minus g of a would still give the area in between. If g of x is the area from c to x, g of b minus g of a would also give you the area in between. So if you have the antiderivative, this antiderivative would be like antiderivative at a particular point x would be this. I'm adding a c because we don't know the from point. The y-intercept is unknown. So if we expand this, the two c's cancel out. Plus c, and then plus c again. Yeah. The two c's cancel out. And that gives us this, which we know is the area between A and B. So we don't have to know the original. We don't need this lower bound. Simply taking the antiderivative would work. And that is the second fundamental theorem of calculus. Okay, so over here, so they basically introduce the average value, what I said over here, and then they use the same proof I do, I think. No, this is for the mean value integral. Average value of a function. Yeah, so they gave the integral here. So f of c is the average value on between 0 to 3. So what would be the average value? It would be 9 divided by 3. No, wait. Wait, am I wrong? This is the average value. Yeah, f of c would be 9 divided by 3. Oh, we have to find c. So yeah, the value of c would be root 3. This is the first theorem of calculus. If this is the area, then the derivative of this is f of x. And then the second theorem of calculus is, yeah, this is the antiderivative. Finding the area between a and b. You can do this simply by using the antiderivative. You don't have to know the area function. Should I do some questions? Let's see. In the following exercises, use the fundamental theorem of calculus part 1 to find each derivative. So let's see. I have an area function. Let's use x. E to the power of cos t dt. So the derivative of this would be the original function with the value x. Oops. Let's see. 149. This answer key is not even loading. Let's see what the... I also did the next chapter, but I deleted that stream. Integration formulas and the net change theorem. Oh yeah, the total integral. So the integral of this and the integral of this. Since this is minus area, this minus this would give you the net area. So basically area of this is 80. Area of this is 30. So you are integrating both of them, won't give you 80 plus 30. It will give you 80 minus 30. It will give you the net area. Integrating even and odd functions. Oh yeah, for this. For even function, this side and this side would be like a reflection. Basically, if you have something like this, it's not even drawn properly. Yeah, never mind. If you want to find if you want to find the area over here, all of this, the total area would be like area of this side times 2. So the area from minus a to a would be the area from 0 to a times 2. And for odd functions, let me just remove this. For odd I think the picture makes the website slow. For odd function, if you have something like this, so it's like this and this, there's a reflection. No, wait, there's a reflection from y is equal to x line. So it's like I don't know if here, here. So if I do a minus a, the area over here would be equal to the area over here. So this, so if you take the integral of both, you will get 0 because the net area is 0. So area over here minus the positive value of the area here. Okay. Let's try. Let's see. Let's try. The antiderivative at x. Let's try this one. 1 over 2x. There. So is there a symbol for, and I guess this is the symbol. If I derivate this like that, but to the power of 0 it will be equal to 1, right? Or no, if I do ln of x, the derivative of ln of x is 1 over x. The derivative of ln of 2x will be 1 over 2x. So the derivative of the outside times the inside. Wait, is this correct? That will give us 1 over x back. Hold on. Oh yeah, that makes sense, I think. Because then this is equal to ln of yeah. Since this is like a the derivative at each point, the gradient at each point will remain the same for both ln of 2x and ln of x. This is like shifting ln of x a little bit up because you're adding, because it's like the original function plus ln of 2. So the gradient would be same. So that makes sense. But I don't want them to cancel out though. So, of course, plus C. Okay. Uh, hmm. Or maybe if I do times half, the derivative of this is just 1 over x. I think it's half ln of x. Let's see. Answer key 209. Hold on. Alt. Hold on. I just need to check one thing. Okay. Alt. Yeah. So for 149, it's e to the power of cos x, which we just did. And 207, no, 209. Yeah, it's half ln. Oh, also I keep forgetting. It's ln. No, sorry. Yeah, modulus. Wait, hold on. Ln modulus of x goes over the entire domain. So the derivative, wait, if I do 1 over x, hold on. I'm slightly confused on why antiderivative of 1 over x is ln of x, ln of modulus of x. I did this. Yeah, this would make sense. This doesn't make sense. Okay, should I do the next chapter? substitution. This is where it gets hard. The fundamental theorem of calculus gave us a method for evaluating integrals without using Riemann sum. The drawback of this method, though, is that we must be able to find an antiderivative, and this is not always easy. In this section, we examine a technique called integration by substitution to help us find antiderivatives. Okay, let's see what they did. We are looking for an integrand of the form f of g of x times derivative of g of x d of x. For example, in the integral x squared minus 3 cubed to x, we have f of x is x cubed and g of x is x squared minus 3. The method is called substitution because we substitute a part of the integral with the variable u and part of the integrand with du. It is also referred to as change of variables because we are changing variables to obtain an expression that is easier to work with for applying the integration rules. Okay, so it's in this form. F of u du. So this gives the antiderivative plus c. Let's see the proof. F g of x, derivative of this, integrating both sides will give this. If we substitute u is equal to g of x and du is derivative of g of x is equal to dx, we get so f of u du, f of g of x plus c. I think this representation is very confusing. I need to do some exercises. They should hide the analysis as well. Okay, using substitution to find the antiderivative. Let's see. So the antiderivative six x 3x squared plus 4 to the power of 4 dx. Let's erase this. So the derivative three x squared plus 4 is 6x. Wait. Hmm. actually. No. Hmm. So and then this is equal to uh, f g of x plus capital F, right? So the antiderivative. What is capital F? No. This. So g of x 3x squared plus 4 to the power of 5 over 5 plus c. Yeah, this is the answer. This was really confusing. Unless there's a u I could use. How do I represent it like this? Uh, me use like the entire thing. If I do u is equal to 6x 3x squared plus 4. Six times 4, 24 derivative of the outside times the derivative of the inside, right? Right or wrong? Um, Derivative, no, wait, sorry, it's wrong. Derivative of the first times the second plus the first times the derivative of the second. Derivative of the first times the second plus the first, which is 6x times the derivative of the second. Uh, this is getting more complicated. What if I choose u as just this? Hold on. Three x squared, which is 6x. Um, hmm. And if I bring this to the other side, oh wait, now let's think about this. No, this is 1 over 4. So if I bring this to the other side, you will have 4 here. If I bring this to the other side, yeah, this 4 become 3. So I can write u over 4 is equal to so going back to the area, u over 4 du. This, if I evaluate this, so I can take 1 over 4 out. U square plus 2. This is plus c. Is this even correct? U squared divided by 8. What is the original answer? This. I don't know. But u square, like this square divided by 8 doesn't give this answer. Unless I'm missing something. Derivative of the outside times the derivative of the inside. So dx the other side. 4 on this side. I think. Wait. If I multiply this side by u to the power of 4 divided by u to the power of 3. This cancels out, so you're left with this. This goes to the other side. It's not u to the power. Yeah, I made a mistake here. So like this. And then this becomes u to the power of 5 over 5, which becomes u to the power of 5 over 20, which is also wrong. Why didn't this work? I have no clue. Next question. Using substitution rule with alteration. Z to the root z square minus 5. z square minus 5. So let me see. Derivative of z square minus 5 is 2z. Uh, hmm. Derivative of z is just 1 also. This is with respect to z. The problem is finding the right u. Okay, let's try derivative of c square minus 5. Derivative of this is derivative of the outside. Times the derivative of the inside, which is 2z. Okay, how about this? We do cube root. So the derivative of the... So it's like to the power of 1 over 3. No, wait. Not cube root. Three over 2, I think. Let's derive this. This gives... If I subtract 2 over 2 from this, I get half. And then 2z. 2 and 2 will cancel out, so I'll be just left with z. But there's a 3 here. So if u is equal to z square minus 5, 3 over 2, derivative of u would be this 3c root z square minus 5. So 1 over 3 du dz. This is with respect to z. So in the antiderivative function, I can just write this, which will then give me u over 3 plus c. Is this correct? Yes. If I expand u, it's e square minus 5 3 over 2 to the power 3 over 2. Using substitution with integral functions, trigonometric functions. sine t divided by cube cos cubed cos t cubed dt. So let's say derivative of cos squared. No, I think 1 over. No, not 1 over. Yeah, minus 2t. So the derivative of the outside will be cos minus 3t, and then times this by negative 2, and then derivative of the inside, which is cos t, is minus sine t. So u is equal to, I think this is a good choice. To sine t, well, cos cubed t. So the area function, so the, I mean, technically it does give the area. Antiderivative function is du. I bring dt to this side and 2 to that side. No, not, it's half du. And then this is plus c. Let's check. U 2 times cos square t. My u is 1 over cos square. Okay, this one looks difficult. What are they saying here? Sometimes we need to manipulate an integral in ways that are more complicated than just multiplying or dividing by a constant. We need to eliminate all the expression within the integrand that are in terms of the original variable. When we are done, u should be the only variable in the integrand. In some cases, this means solving for the original variable in terms of u. This technique should become more clear in the next example. Finding an antiderivative using u substitution. So what are they doing here? Antiderivative. So the integral x divided by x minus root x minus 1 d of x. Let's say, let's find the derivative of this. So half will become minus half. Right? And then derivative of the inside is just 1. Let me think about this. I have no clue. Wait, hold on. Hold on a minute. If I do u is equal to root x minus 1, then u squared plus 1 is equal to x, right? And the derivative of u is equal to 1 over 2 u. So that means 2u derivative of u is equal to d of x. So going back to our area function, we can replace d of x with 2u du, right? Du. We can replace x with u squared plus 1. We can replace this with u. And then this is equal to u when u cancel out. And I can bring 2 outside. And then this is equal to, if I evaluate, this gives u cubed over 3 plus u plus c, where u is equal to root x minus 1. Let's see. Did I get this correct? 2 over 3 half. Okay, 2 over 3. Okay, so the 2 is correct. u3, wait, let me evaluate this. So this gives 2 over 3 x minus 1. Since it's a root, it will have this, and 2 x minus 1 to the power of half plus c. Is this correct? Yeah, I guess so. For the definite integrals, we need to substitute the value. What is the next chapter? I think these two I should leave it for the next stream. I should do one more and then I think I will end the stream. In the following exercises, use a suitable change of variables to determine the indefinite integral. Let's try this. No, wait. Let's try this. t square cos t square. Um, Derivative of sine t square is equal to derivative of the outside, which is cos t square, times the derivative of the inside, which is 2t. Hold on. If I do u is equal to sine t squared, the derivative is this, right? So I can do this. Like that. Oops, wait. So now going back to the area function or the antiderivative function. I can replace this, and this with half du. Then replace sine t square with u, and then I can bring the half outside. Then I get u square over 2 plus c. What number is this? 279. 279. U is sine t square. This answer should be correct. U square over 4. So sine square t square over 4. Sine square t square over 4. Or why did they get like minus? If I don't use sine square, if I use cos square, I will get minus. If I use cos t square, I will get minus sine t square. Then there would be a minus half here. Then sine t squared times t dt. Then I can replace this, and this with minus half. Yeah, that would make sense. Right, I guess I will end my stream here. Also, if someone can explain me this, like ln of modulus x. Y is the antiderivative 1 over x, and the derivative should be same on both sides, right? Okay, I will end the stream here. Wait, and I guess I'll see you guys next time.